Hello and welcome to Mrs. Ballard's class. Today we're going to be talking about, I keep doing that, the calculus topic 1.9, which is connecting multiple representations of limits. If you have not gone and done the note page yet on your own, you really should try it. You really don't need a lot of instruction on this, but I will go over the answers really quick, so that way you can make sure you did it correctly, but you really should pause and do that first. So our question or our objectives for the day is the essential question is what are the similarities and differences in the graphical and analytical approaches and limits? And I can identify similarities and differences between graphical and analytical approaches to limits. Okay. All right. Don't forget to put your name on the page. So let's do that first. All right, and then I picked this Bitmoji because when I started typing up infinite, it came up, and and I put infinite pets because it wouldn't let me do very many words. But I liked the Bitmoji had a very weird look on her face because she had so many pets. We don't have any pets in the Ballard house, but not that my 4 children wouldn't like them, but we don't have any. So, although my third child loves to pretend to be a cat. All right, let's take a look at these really quick because you should have hopefully done them. So we're going to go over them. So the first one here, and I'm going to try to write tiny so I can get it squished in there. We have the limit as x approaches -2, and I'm just going to put f on top of g, so x squared minus x minus 6 over x plus 2. And you'll notice that we can't put a -2 in there, which means I probably need to factor this thing, and I have to keep writing that limit notation out front until I've actually taken the limit. So it looks like I need a good old magic x. I'm going to come over here and do my magic x. I need two numbers that multiply to -6 and adds a -1, which are 3 and 2. 3 is negative, so we've got x minus 3 times x plus 2. And yay, my x plus 2's cancel. So I have the limit as x approaches -2 of x minus 3. And I can direct substitute in -2 minus 3 is -5. All right, this time I have to put g on the top and f of x on the bottom, and we're approaching 3 this time. I'm going to go ahead and use the already factored form for my f. Oop, I forgot my limit. So we've got the limit as x approaches 3. The g is x plus 2, and the factored form of f is x minus 3 times x plus 2. So I'm kind of skipping a step. I know I can't put the 3 in there because it would make it 0. So luckily these cancel. Okay. I don't think that really helped me though, did it? Because I really would have needed the 3 to cancel for me to be able to direct substitute in. Because I still can't direct substitute in. So when I hit something like this, what I start to do is I go back to the numerical approach where I'd use a table. And I know from doing all these tables that it always ends up being whatever the last numbers are, right? So I could just look at a number just really, really close on that side and like really, really, really close on this side. And I could put that into my calculator. So I happen to have my calculator, I think, set up for this. I think I've got Desmos set up for it already. Let's see. All right, so there it is. I'm going to put in my 2 point and I can kind of watch it grow. So it looks like, look at how gigantic it got really fast. So that means, or actually it got really small really fast, because that's like going to negative infinity. What happens if I go the other way? The 3.01, and then I keep putting zeros in front of it. Look, and now it goes to infinity. And this is just this other notation here. It's scientific notation, meaning the computer couldn't handle any more zeros. So I'm pretty confident that that's going to go to positive or negative infinity. In fact, I could cheat and look at the graph and I'm seeing, oh yeah, it's going to negative infinity and positive infinity right there. There's an asymptote. So we're going to go ahead and write that down. Oh, wrong document. There we go. So we would want to say that, and then I'm going to put a little arrow. This means the word implies, okay? It implies that it's going to negative infinity or positive infinity, so therefore the limit does not exist. All right, now we're doing g of x over h of x, so we're switching functions. We're doing these two. So I've got the limit as x approaches -2 from the right. I really should have used a different color. Let me go and do that. And I'm going to write a little lower. So the limit as x approaches -2 from the right of x plus 2 over -3 absolute value of x plus 2. All right, so we've seen that absolute value before, and we know that we're coming at it from the right, which means we want the positive absolute value, because typically we break that up into a positive and a negative. So I'm going to get to break that up. So limit as x approaches -2 from the right of x plus 2 over -3 times x plus 2. Now I'm allowed to cancel that. So only thing that I'm left with in the numerator is a 1, so my limit has to be -1/3. Okay, now we are looking at this graph over here. It says it has a vertical asymptote at -4. It doesn't hurt. If you want to sketch that in there, go ahead and sketch that in there. Okay. All right. We're looking as x approaches 1. So as I'm approaching 1 from the left and I'm approaching 1 from the right, it appears that they're both going. It doesn't look like it's quite at 4, does it? So I'm going to just estimate 3.7. If you want to write 4, that's close enough for this one. All right. We're now looking at 4. So let me erase a little bit. And as we approach 4, as we approach 4, it doesn't have the same right and left hand limit. So we would say that this one does not exist. Oops. Okay. And then as we approach 4 from just the right side, so if we're just coming at 4 from the right side, it's going this direction, which means its x value is -2. And then we're now looking at -4. Ooh, -4 goes this direction and that direction. So, and because of that vertical asymptote, we know that the limits are going to be opposite of each other. So to jump plus, they're increasing it without bounds. So this is definitely a does not exist, because your right and your left do not match. All right, and I know this part might have been a challenge, but let's kind of think through it. You guys probably haven't done one of these on your own yet, where you've got to graph it. So first thing you do is you just start with an XY axis. It's sloppy. It does not have to be perfect, okay? Then the next thing I always do is I look for if I have any coordinate points. And in calculus, we don't write our coordinate points like this anymore. We write them like this because this is too hard to confuse with interval notation. So this is really saying that my x value is -1 and my y value is 0. So I could plot that. So out at -1, 0 is there. Now I'm going to go back and read and see what happens here. It says that x approaches -1 from the left is at 3. So 1, 2, 3. I know it can't be closed. It's got to be open. It's got to approach that from the left side. So I could draw anything I wanted over there from the left side. X approaches -1 from the right, goes to -2, so I could put an open dot there, because again, it's not closed. There's only one spot where it's closed. And I can draw anything I want from over here. All right, let's look at this one. So look, it's going at 3 from both sides. It's going to different infinities. That's a really good indicator that that's an asymptote. So let's draw that asymptote in there. So 3 has an asymptote. And I know that on this on the left side of the asymptote, it's going down, whereas on the right side of the asymptote, it's got to go up towards positive infinity. Now let's see what's happening here. As we are approaching, as x is going to negative infinity, that means as x is going to the left, the y value is 3. So that kind of seems like another asymptote. I'm going to go draw one there, even though I don't really need it necessarily. Okay, so it looks like I've got a good curve coming here. That should be curvy, not pointed. All right, and then this one says that as x goes to the right, it goes to positive infinity, my y value goes to -3. So I could draw a -3. I could draw kind of another asymptote right there to help me draw it. So it looks like we're doing something along those lines. Again, it should be curved. All right. Then it says, number 1 in this last box here, which limit from box B does not exist for the same reason as in problem 2, box A? Well, there's only one that doesn't exist here. And we know it doesn't exist because it goes to either negative or positive infinity. So so we know that that's an indicator of an asymptote. The only one that has an asymptote here was where x was equal to -4. So it has to be problem number 4. And I would say if you want to write down a note is because of the vertical asymptote, or that it goes to negative or positive, or limit equals negative or positive infinity. We're now supposed to sketch a graph again. So we're going to sketch a graph of the limit described in box A number 1. Well, if I look at this here, notice this is what it reduces to. So it's just a line, but when I canceled here, I ended up having a hole in the line. If you've hopefully seen that before a little bit, and I know we're going to get into it in a couple lessons here, so we're kind of previewing a little bit. So my hole, though, I take what I canceled and I set it equal to 0. My hole is at -2. So I'm going to draw the line x minus 3. So I'm going to go to my y-intercept of -3. I'm going to go up 1 over 1 a couple times. And then I'm going to come down the other direction. But I know at -2 there is a hole in it. So it's going to look something like that. And using number 1 in box C, explain the difference between the limit as x approaches -1 of g of x and g of -1. All right, so I'm going to give my best shot at this. So when we find g of -1 is finding what the y value equals when x equals 1, but finding the limit as x approaches 1 of g of x is finding what the y value approaches, not is equal to, but approaches as the x value approaches 1. And that's the end of our lesson today.